If you think you know how the universe will end, you're probably wrong. This is because no one knows for sure what the future holds. The options seem endless, from big wrinkles to big tears, from cyclical awakenings to endless darkness. But this does not mean that predicting the end of the universe is beyond the capabilities of science. By learning more about the universe around us today, we can discover what will help us predict its eventual destruction. You are looking at space theory. Join me today on a journey into the future of the universe. A future where there are no more planets, stars, or galaxies, no more atoms or molecules or life. A future where the universe is on its deathbed. How much time do we have until the future? And does the universe have an afterlife? These questions may sound impenetrable, but the answers to them lie in our understanding of nature's best-known force, gravity. Normally, gravity is an attractive force that slows down objects that are trying to move away from each other, or speeds up objects that are getting closer. Therefore, before the discovery of dark energy, astronomers assumed that gravity would slow down our expanding universe over time. They even invented a parameter called Q to measure its rate of deceleration. But at the end of the 20th century, supernova measurements showed that Q was actually a negative number. The universe wasn't slowing down at all. It sped up. This acceleration is fundamentally related to the type of matter and energy in the universe. If the gravitational force is created by the energy of ordinary matter, it must use a completely different form of energy to explain the gravitational force that accelerates the expansion of our universe. We call this form of energy dark energy. The hard part is that we don't know exactly what dark energy is or where it comes from, and yet the fate of the universe is tied to its identity. Depending on the nature of dark energy, the accelerated expansion of our universe may accelerate, settle, or even reverse course. Instead of making a video about just one of these fates, we decided to put them all together into one big flowchart that acts as a single guide to the end of the universe. At the top of the flowchart is dark energy, and at the bottom, how we all die. Most cosmologists agree that dark energy probably falls into one of two main categories. The first, the most popular theory, is that dark energy is the energy of the vacuum itself. The second, the main option, is that dark energy is the energy of new fields in the universe that we simply haven't discovered yet. Since fields are just a collection of particles, this would mean that dark energy consists of a new form of matter, a new kind of particle beyond electrons, quarks, or anything else we know today. From these two categories, our flowchart branches off to dark energy theories, which vary widely and predict all sorts of catastrophic futures. On the vacuum energy side, we need to consider whether the vacuum itself is stable, or whether it can jump to an even lower energy state through a process known as quantum tunneling. A stable vacuum is the simplest scenario. This means that dark energy will exist forever in the same form as it is now. Our universe is forever accelerating, becoming infinitely larger and colder in the so-called Big Freeze. The good news is that you wouldn't change anything here on Earth, or even in the entire Milky Way, because there is enough mass concentrated in this small area to resist the gravity caused by dark energy. But if you zoom in further, you'll find that distant galaxies are being accelerated away from ours in all directions, eventually crossing a threshold known as the event horizon. Just like a black hole, once you cross that point, you can no longer interact with the world you left behind. This means that one by one we will lose contact with everyone outside the local galaxies where gravity is strong enough to hold us close. All that remains of them is a fading, reddened light from the moments before they crossed the event horizon. Eventually, that light will become so dim that it too cannot be detected, and future generations of astronomers, billions of years down the road, may have no idea that anything outside the Milky Way ever existed in the universe. If you want to know what happens to things inside the Milky Way, it dies a relatively boring death. The second law of thermodynamics states that systems always tend to states of higher entropy. When stars fuse hydrogen into helium and emit light as a byproduct, when planets heat up and winds rise through the atmosphere, and even when you eat a carrot and wait for it to come out the other side. All of these processes add entropy, but the entropy of the Milky Way can only grow so much. Eventually, the stars run out of hydrogen to fuse, the planets are left to freeze, the winds wither, and there are no more carrots to melt. Matter has nothing to do but collapse into black holes, and the black holes evaporate into a pool of radiation. What we once called the Milky Way is in perfect thermal equilibrium. Nothing will happen. Nothing will happen. The fate that awaits the Milky Way is sometimes called heat death, not because of heat, it is actually quite cold, but because there is no more heat, there is no temperature gradient, there is no transfer of energy from one place to another. Heat death can take time to reach, however. Some estimates put it at 10 to the power of 106 years, or 10 to the power of 96 times the current age of the universe. But if dark energy really comes from a completely stable vacuum, it cannot be stopped. Heat death is coming. However, there is one possible silver lining at the end of this story. Sir Roger Penrose, Nobel laureate and brilliant physicist, thought that heat death might not be the end of our story, but only a new beginning. In his model, known as conformal cyclic cosmology, Penrose proposes that a radiation-filled universe in the infinite future is indistinguishable from the state of the universe at the time of the Big Bang, and that they may indeed be one and the same. Each aeon of infinite expansion in this model only leads to a new Big Bang and a new cycle of cosmology. There is still not much evidence to support this hypothesis, but it may be a source of hope that our universe is on its way to a big freeze. You and I wouldn't make it, but maybe the universe could, and that's at least something. If the thought of the big freeze scares you, I have good news and bad news. The good news is that there is reason to believe that even if dark energy originates in a vacuum, that vacuum may not last forever, which means we may not be headed for the big freeze. One reason to doubt the stability of the vacuum comes from observations of the Higgs field. Current measurements at CERN indicate that the Higgs vacuum may be lower than the one we live in, although tunneling into that preferred vacuum may take about 10 to the power of 100 years. To paint a picture of how all this works, we can imagine an apple falling from a tree, hitting our friend Isaac on the head, and rolling onto the grass in a small drop. A short distance away is an even larger pit, to which the apple would certainly have gravitated had it not been for the obstacle in its path. Classically, the apple is stuck, but quantum mechanically, the apple can tunnel through the barrier into this lower energy state if you wait long enough. The Higgs field works similarly, and its different vacuum states correspond to different grass closures. Another reason to doubt the stability of the vacuum actually comes from string theory. Although string theory didn't make any quantitative predictions, it gave us pretty strong hints that positive energy stable vacuum states are really hard to find. The language theory also predicts the existence of new fields that could change to different vacuums much faster than the Higgs says over the next trillion or even 100 billion years. Here comes the bad news, though. If we live in a metastable vacuum that can break apart at the whim of quantum mechanical oscillation, we have bigger things to worry about than the big freeze. Quantum tunneling into a more stable vacuum not only affects the expansion of space, but can also fundamentally change the properties of particles and the laws of physics that govern our universe. When the Higgs field collapses into a new vacuum, ordinary particles like protons and electrons have a completely different mass, and atoms and molecules as we know them cease to exist. Or if we tunnel into a new vacuum in the landscape of string theory, our universe might suddenly contain new particles we've never seen before. Either way, life on Earth would definitely be toast. As for the universe as a whole, in this scenario, we cannot predict its fate more precisely without more information about the new void we are entering. Let's step back and look at the other side of our flowchart, where dark energy comes from the presence of new fields instead of a vacuum. Fields can develop in different ways over time, which in turn determines the future development of our universe. Unlike vacuum states, whose energies would be completely constant between tunneling transitions, fields can continuously gain or lose energy over time. Just as a ball rolls over rough grass, fields can roll over undulating potential, transforming dark energy with each step. The fields can even change their direction of rotation, meaning that a previously repulsive force of gravity can become an attractive force. It's called the quintessence, and it opens up completely new possibilities for the future of our universe. The three main cases of quintessence are 1. The case where dark energy remains constant over time, 2. The case where dark energy decreases, and 3. The case where dark energy becomes stronger. In the first case, we return to heat death. Otherwise, we might have another big crunch. Dark energy slows down and eventually stops accelerating the expansion of our universe. Gravity takes over, and pulls everything back towards a single point in a fiery collision, back to the original singularity that started the Big Bang. It's an incredible apocalypse scenario where time itself ends. In the third case, we have a big tear ahead of us. As the repulsive force of dark energy grows, galaxies, stars, planets, and even atomic nuclei are torn apart by the relentless expansion of space itself. This terrifying possibility gives us the shortest possible timeline for doomsday. Some estimates suggest the Great Rift could hit us in as little as 22 billion years. Fortunately, current observations do not support this theory, but the possibilities of dark energy leave no room for certainty. Let's look at our last flowchart. Whether the universe ends in a heat death, a big crack, a big tear, or a complete restructuring of the laws of physics, the end of the universe is sure to be spectacular, terrifying, and thought-provoking. And as we learn more about dark energy, our fate becomes a little clearer and closer every day. How do you think the universe will end?